Okay, now that we have seen how the computer can compute a change for a different color by performing binary addition, let's take a look at how this is applied to photo image processing. In this example, we'll make some changes to a black and white photo of the moon that we have scanned into the computer. Now the techniques we're going to cover would be the same for color image, but black and white is a good abstraction to remove unnecessary complexity and still serve the same goal of teaching the principle. So remember that if this is a black and white photo, all of the pixels to display the image on the computer screen are either black, white, or shade of gray, which also means that the amount of red, green, and blue intensity in each pixel is equal to one another. So let's say that we want to correct a smudge on the picture that was created by scanning a black and white photo into the moon, of the moon. The smudge was caused by something that got onto the glass of the scanner. Now the smudged areas of the picture have a dark gray value for the red, green, and blue light intensity. We'll say they have a decimal value of 28, which is close to zero, relatively close to zero. So while it's not quite dark enough to be black and not be noticeable, we need to now get the computer to basically go through each of the pixels, looking for the values that would represent close to zero but not quite at zero. And the way we would do that is, if you recall on the 8-bit binary assignment, that the first bit is worth 1, the second one is worth 2, the third one is worth 4, 8, 16, and 32. Now any of these together would give you, could give you a value in the range of 0 to 63, which is still fairly close to 0. If 255 is white and 0 is black, it's still closer to black than it is to white, any number between 0 and 63. So the bits that would actually set it closer to white would be the leftmost bit, which is 128, and the next one, which is 64. And so what we need is basically the computer to go through looking for bit 128 and bit 64 to see if they are 0. And if they are, it's close to whatever the rest of the bits are, it's close to 0, so just zero out the rest of those bits. And by doing that, you actually remove the smudge from the photo. All right, so moving on, let's say we want to process the image by colorizing it to a shade of orange. If we look at a shade of orange, for example, the red might be 255, the amount of green is 213, and the amount of blue is 132. What we are going to do then to start this colorization process is locate all of the white pixels. Again, those would be pixels with 255, 255, 255 for the red, green, and blue, and replace them with 255, 213, and 132. And this would change all the white pixels to this new shade of orange that we want. But it will not change any of the gray colors of the photo. So what we would need to do is basically get the difference between the white and our new replacement color for white. And we wouldn't have to worry about red because it was 255 in white and 255 in this new orange color. But the difference between the amount of green would be subtract 42, and the amount of difference between the blue that we had and the new color that we're using is a difference of minus 123. So again, we would go through looking for all of the gray colors, then subtract 42 from the amount of green and 123 from the amount of blue, thereby tinting all of the grays towards an orange. What we'd end up with is something then that looks like this. On the left is the original black and white photo. On the right is the orange tinted version of the black and white photo. All right, so now let's take a look at how the sound information is digitized and represented in the computer. First, what we need to do is review some basic physics of sound waves. Sound is created when some object causes air pressure to begin vibrating between positive and negative air pressures. And that is represented here by a sine wave. And what we see then is the amplitude of the sine wave rising above the zero reference, then going below the zero reference, and then returning above the zero reference. The distance from the top to the bottom of the sine wave is referred to as the amplitude, and it's perceived by our ears as the volume of the sound. And then the frequency, meaning the amount of time it takes for the air pressure to increase above to its maximum, return to zero, go to its negative, and return back to zero. How fast that happens per second, which would be the frequency, is perceived by our ears as the pitch of the sound. Now, since sound waves are continuous and we cannot represent the entire spectrum of information of the physical phenomenon of the sound wave in the computer, it has to then be transformed from an analog, which is the physical world, to a digital value, which is the computer's world. And this is accomplished by measuring the amount of change above the zero line on the graph and the amount below the zero graph on the line. And we do that by measuring at regular intervals to find out what the value is. So here are two different rates as an example of sampling. The area outside the rectangle represents the sound information. So as we look here at this rate number 1, we see that some information is outside of the rectangles for the sample, which means it's information that's actually lost. If we sample more often, then the amount of information that's represented outside of the rectangle is much less, as in rate number 2. So as a result, in general, the faster that we do the sampling, the more accurately we can represent the sound wave that we are recording. On the other hand, if we sample too fast, we end up with larger amounts of data representing the sound wave than humans actually need to perceive it with our ears. So a scientist by the name of Harry Nyquist worked out a fairly simple rule to solve the problem of how fast sampling rate is needed. The rule is simply that the rate must be at least twice as fast as the frequency being sampled. Now, since human hearing is in the range of about 20 hertz up to 20,000 hertz, if sampling is done at least 40,000 times a second, it'll be fast enough to capture what humans would be able to hear. Anything faster than that would be wasted on us humans. I guess it would be useful for dogs who can hear up to 45,000 hertz. But that's the idea behind the Nyquist rule. So as a result, standard digital audio recordings are done at 44,100 hertz. The 100 hertz is basically for technical reasons. We add some additional speed in terms of our sampling rate. Okay, so the process of digitizing is accomplished through the use of a transducer called a microphone, which converts the sound wave to an electrical wave. Now, the electrical wave is converted at regular intervals into binary numbers and then saved in the computer's memory. The common term for this is called an analog to digital converter, or A to D converter. And then the reverse process is digital to analog conversion, which converts the bits from memory into electrical signals, and then through the use of speakers converts the electrical wave into sound waves. Now, the last issue to consider is the number of bits used to save a sample, which determines the accuracy of the representation of the sound wave information. Again, the more bits in general, the better the accuracy, but also it results in larger completed files when we're done recording. So typical sample sizes are based on 16-bit samples, which will allow us to record 65,536 different levels of sound, and that would be 32,000, that's half, 32,768 above the zero reference, and negative 32,767 below the zero reference line. Now, to better understand this, let's use a smaller sample size. So to illustrate this, look at a sample size on the left where we have only 3 bits of precision, and on the right we have 4 bits of precision, so just one more bit of precision. And the difference in just between 3 and 4 is that in 3 we only have 7 different levels that we can record, if you include 0. And on the right, by just increasing the precision by 1 bit to 4, we get 15 levels that we can represent between the maximum and 0 and the negative minimum value. Okay, so the last part then is to talk about how it is important to understand how the technology of recording sound has evolved into what we do today. For example, it's very common for people to download music from various web services such as iTunes or Rhapsody or Spotify, maybe even Amazon. This technology would not be possible without the ability to compress the sizes of these music files so that they can be downloaded quickly over the internet. Now, the de facto standard compression algorithm for digital audio is called MP3. And MP3 is referred to as a lossy data compression. I'll explain more about data compression algorithms. There are lossless and lossy data compressions. And this one works by reducing the accuracy of certain parts of the sound that are recorded, which are considered to be beyond the auditory resolution ability of most people. The compression generally allows the raw sound file to be compressed to a ratio of about 10 to 1. This allows a sound file, say, of 1 megabyte to be compressed down to 100 kilobytes, which is drastically a drastic improvement in the amount of time that it takes to download over the public internet. Without the ability to compress these sound files and the ability to download them quickly over the internet, there would be much less commercial use of the internet today, since so much is based on video and audio compression techniques. So let's continue to look at issues related to compression of information. Here we're going to consider an 8x10 color image that we've scanned at 300 pixels per inch. That's linear, 300 pixels per inch. This image would require 21.6 megabytes to store in the computer. Let's take a moment to calculate why that is true. I'm going to pull up the calculator here on my computer and just walk through this quickly. So if we're scanning this 8 by 10 inch color image at 300 pixels per inch, that's 300 pixels times 300 to get square inches. And 8 by 10 is 80 inches. So this is 90,000 pixels per inch, and we're going to multiply that by 80 inches. And then it takes 24 bits to store each pixel. Again, that's 8 bits of red, 8 bits of green, and 8 bits of blue information. So we'll multiply this by 24. And so this is how many raw bits it takes in order to store this 8 by 10 color image that we scanned at 300 pixels per inch. Next, what I want to do is divide it by 8 so that we can figure out how many bytes it takes to store this. And it comes back at 21,600,000 or 21.6 megabytes to store this one image. And that's quite a bit of memory, but it's really a problem when you talk about transmitting this image over the internet. Now, a 56 kilobits per second modem is an old technology, but I want to use it because it really gets the point across of why compression is so important. So, if we had a 56 kilobits per second modem to download this image that's 21.6 megabytes, how long is that going to take us? Well, again, we can make a quick calculation. I'm going to convert the megabytes back to bits by multiplying by 8. So that's how many bits it takes to store the image. And if we have a 56 kilobits per second modem, that means we can download per second 56,000 bits. So I'm going to divide that by 56,000, and that's how many seconds then it would take for us to download this image. I'll divide it by 60 so we can get minutes out of this. So it'd take almost 51 and a half minutes to download this picture over the internet with a 56 kilobits per second modem. And that, of course, would not be acceptable today in terms of the download speeds. In fact, the question is, how can we see screen size pictures then in just seconds while surfing the web if it takes 51 minutes to download? Well, the answer is that we use JPEG compression in order to compress the size of the images down to much smaller sizes so that we can download them quickly over the internet. So let's take a look at that. Before I get into the JPEG, I do want to spend a moment explaining the importance of the two main types of compression algorithms. They are lossless and lossy compression algorithms. We talked briefly about a lossy compression algorithm for audio. Let me give you the comparison of the two. Lossless algorithms would be like zip files, where it's essential to be able to reproduce the original data perfectly. As an example, bank account files or text information need to be able to be reconstituted in their original form perfectly with no lost information. In contrast, lossy algorithms compress data by discarding or losing some of the information that is considered not essential. This type of compression is most commonly used with multimedia data, such as audio, which we saw with the MP3, video, which we'll see in a moment, and still images, which the JPEG is an example of. So that brings us back to JPEG. So JPEG, which stands for Joint Photographic Experts Guild, is a lossy compression algorithm used on still images. And the idea is that small changes in hue or gradation of color is not noticeable by our eyes. And by discarding small changes in hue, we have fewer pixels to save in the image data that we use, and we can get as much as a 20-to-1 compression ratio without us even being able to perceive the difference between the full, what we'll call the full color image and the JPEG image. To illustrate this, let's take a look at 3 examples. The first one is A, and that is a full resolution image of a flower. B is a 45-to-1 compression, which we can hardly notice a difference between A and B. And yet C is a 125-to-1 compression ratio, and we can certainly see through pixelation that the image is noticeably different from the original. So the amount of compression that we can get away with is somewhere on the order of 20-to-1 up to 45-to-1 in terms of the compression ratio. The Motion Picture Experts Guild created a similar compression standard called MPEG. MPEG 2 is the current de facto standard. And this is a lossy compression algorithm which uses the combination of JPEG-like compression as well as interframe coherency. This means that only differences between frames is encoded. And with this, it results in a huge compression ratio. And again, without this, we wouldn't have the streaming services like Netflix and Hulu and some of these other even on-demand type of downloads that we can watch movies and television shows. Looking over the previous chapters, we should now be able to see that bytes of binary data can represent many different kinds of information. We've talked about ASCII characters being represented, decimal numbers, colors, audio, still photo images, as well as motion picture images that can all be represented by binary data. This is a fundamental property of information technology which can be summarized as the bias-free universal medium principle. What it basically means is that bits can represent all kinds of discrete information but have no inherent meaning of their own. The old saying that I always heard was bits are bits. They're not binary numbers, they're just bits. They represent whatever it is that we interpret them to mean. So again, the universal medium is that everything can be represented in a sensible way and then can also be manipulated. The meaning of bits comes entirely from the interpretation placed on them through our programs, and bits can be interpreted as binary numbers or not, depending on how they're being used. For example, we have in this slide we have 3 binary numbers, actually 4 bytes of binary numbers, 2, 3, and 4. And this could represent any of these things. It could be a decimal value. It could be a color in the form of red, green, and blue. It could also represent, as we talked about in computer operations, an operation code for adding a couple of numbers together and then storing them in a random access location in memory. It could represent a group of ASCII characters. Could represent sound samples or an internet protocol address, which we'll talk about later. And of course, it could also be representing a group of hexadecimal numbers. So in summary, red, green, and blue colors, each intensity is a 1-byte numeric quantity represented as a binary number. Binary representations in binary arithmetic are like they are for decimal numbers, but they're limited to the 2 digits of 0 and 1. The decimal equivalent of binary numbers is determined by adding the powers of 2 corresponding to the ones in the binary string. We can use arithmetic on the intensities to compute on the representation, for example, making gray lighter and colorizing a black and white picture of the moon. When digitizing sound, sampling rate and measurement precision determine how accurate the digital form is. Uncompressed audio requires more than 80 million bits per minute. Compression makes large files manageable, like MP3 for audio, JPEG for still images, and MPEG for video. These compact representations work because they remove unnecessary information, because they are lossy type of compression algorithms. The bias-free universal medium principle embodies the magic of computers through the universal bit representations and the unbiased encoding. Thank you.